Welcome back to UVA Data Points. I'm your host, Monica Manning. In today's episode, we're bringing you a conversation with Don Brown, a professor of data science and engineering and the founding director of the UVA School of Data Science, speaking with Bill Basener, a researcher and professor of data science at UVA. This conversation primarily focuses on remote sensing, specifically the use of LiDAR and hyperspectral imaging. Bill and Don discuss the diverse applications of this technology, including how it's used to detect landmines, how it can aid in search and rescue operations, and how it's currently being implemented to help preserve the Chesapeake Bay region. At times, this conversation can be highly technical, but Bill and Don do a wonderful job of placing this technology into a larger context and demonstrating how it can impact and benefit everyone. They touch on environmental science, urban planning, ethics and privacy, computer vision, machine learning, probability models, and much more. It's a fascinating and lively conversation between two skilled researchers. And so with that, here's Don Brown and Bill Basener.
Okay. Hello, everyone. I'm Don Brown. I'm the Senior Associate Dean for Research in the School of Data Science, also a faculty member in the School of Engineering and Applied Science. And I'm here with Bill Basener. And Bill, can you introduce yourself and tell us a little about your background and how you got into data science?
Sure. I'm Bill Basener. I'm professor of data science in the School of Data Science. And a lot of my early work in academia was in math. So my first professorship appointment was as a mathematician at the Department of Mathematics. And I transitioned into data science working with data from a bunch of remote sensing applications that we're going to talk about supporting the U.S. government.
Great. Well, let's go right there then. You said remote sensing. Can you help us understand what remote sensing is?
Yeah, so remote sensing is taking measurements about an object without making contact with the object. So if we have a satellite up in space collecting data about the Earth, that's an example of remote sensing. Or a instrument on a car for us to guide a self-driving car that's examining the world around it. That's another example of remote sensing. Okay.
And what kind of remote sensing work do you do? Do you look at things that are coming from cars, or do you look at things that are that the data is derived from sensors in space, or somewhere in between?
Most of what I do is from sensors that are on board either satellites or aircraft or unmanned aerial vehicles.
Right. And tell us a little bit about the history of this remote sensing area. For, I guess, the vehicular one is interesting, but we think of remote sensing a lot of times with regard to satellites and aircraft. And tell us a little bit about the history of that. How did it evolve, and how did it become something that was important?
Sure. An early example of remote sensing was the U.S. Corona satellite project. So early on, government satellites for looking for nuclear weapons in other countries, things like that. The Corona project was one of the early systems. And so they would actually collect imagery on reels and drop those film reels and catch them with an aircraft and fly them to one of the buildings I used to work with at the university up in RIT in Rochester. And then they develop them. We worked with red, green, blue film, and eventually people realized if you put an extra layer on the film, you could look for infrared light as well. And so things that are painted green that are supposed to camouflage in with plants look very different in the infrared. So you could distinguish between those camouflage vehicles and actual plants by having that infrared as another layer on your film.
So this was obviously a military application. Were there other applications that people were using remote sensing for?
So this early application was a military application. Today, and this is the story of remote sensing, it often gets developed in these military applications when there's a high need, looking for nuclear missiles in Cuba, that kind of a thing, back around the Cuban Missile Crisis days, to commercial applications. Once they're developed, once the technology reduces in price, the sensors reduce in size, it often transitions into commercial application. And that's kind of the story of how I've worked with things, often starting on the government side and then helping transition those things to commercial applications.
Right. And I guess that it's certainly been done by satellites, but I think before that it was done just by aircraft. Is that right?
There was definitely some aboard aircraft, yeah. Yep.
Yeah. And in the aircraft, obviously we're still using aircraft to do it, but we're now starting to use drones. Is that an area that you've been looking at as well?
Yep. We have a drone. So we being my lab at University of Virginia, looking at two types of sensors that are on board our drone. It's a LiDAR sensor and a hyperspectral sensor. And so we collect data with that regularly over at Morven Farms, just south of Charlottesville.
Yeah. And so flying a drone, I mean, that has all sorts of issues for people when they hear about you flying drones and flying over to do remote sensing. So tell us a little bit about the concerns that and how you allay those concerns.
Yeah. So each of the different collection modalities, meaning spacecraft, aircraft, or drones, has a trade-off in what you can collect, how broad of an area you can collect, the resolution of the imagery. And so drones are the highest resolution out of those, but you're restricted where you can collect, right? You can only fly for us, and generally, you can only fly over places where it's approved, right? So not near airports. For us, flying the scientific experiments only over the areas that we've approved to fly over for that day. If you're talking about privacy concerns, right, that's often one of the things people ask with remote sensing techniques. And you're like, oh, you can investigate things that normally people can't, right? So one of the early situations that was elevated to the Supreme Court was Kyler versus the U.S. And the law enforcement used an infrared video camera to look at somebody's attic in their house. And they discovered that the person had a grow lab in their attic from the excessive heat from the grow lights. Supreme Court threw that case out on the grounds that that data would have required a warrant to collect that data, because it collected not only the information on whether there's a grow lab there, but it could have collected other data. So there's these rules for information collection that are really important to both respect, but also respect people's personal privacy in addition to the rules.
Yeah, that's important, obviously. Now, when you collect these data, do you make them available to the public? Are they then put on some sort of open source repository, or put in an open source repository that people can access? And is that typically done by others, I guess? So two questions there. Your data and others' data. Yeah,
it's becoming very common to share the data. So everything we collect on the days that the drone works, because there's some days it doesn't for all sorts of reasons, we share that publicly through our web portal. Mm-hmm. There's the open, I think it's called the Open Topography Lab, where people can collect LiDAR or hyperspectral imagery. Hyperspectral is done through the NASA data portal. LiDAR through the Open Topography. I think we'll probably talk about what those modalities or what those systems mean. But there's places where the data is accessible in general.
Yeah, that's great. I know that from my own work, we did some early work looking at the barrier islands off of the coast of North Carolina and Virginia, but primarily North Carolina, because the concern was the environmental, changes that were happening there. And now, because those data are open source, you can actually see the effects of climate change as you watch the barrier islands. And this, by the way, was done by a NASA U-2, the same plane that you mentioned earlier with regard to the Cuban Missile Crisis. The U-2, of course, is the one that took the pictures. But the NASA has U-2s, and they use them to take for remote sensing and for exactly this kind of analysis, hyperspectral analysis of regions of the country, particularly areas that are threatened now from climate change. So I think it's important that I'm glad to hear that you're making your data available and that others are, because it's important for us to be able to track what's happening. Yep. Let's see. So tell us, you mentioned several times that you've got these multiple sensors. You've got hyperspectral and LiDAR. So why don't you tell us a little bit about what the hyperspectral means? What is that? What is a hyperspectral sensor?
So a standard image that we take with our camera, a digital image, has three values in it: red, green, and blue, right? So we can get the color we see. In our eyes, we have separate red, green, and blue cones. On a computer screen, you put in your red, green, blue values, your RGB values to get color, right? Hyperspectral sensor has 200 or so or more different wavelengths that it collects, right? Red light, what we visually call red light, that is around 650 nanometers in wavelength. Green is 550, blue is about 450. So our sensors go out to 2,500 nanometers. So we get further out in the infrared. And when you have a spectrum, so you collect hundreds of wavelengths of light. When you have that information, you get information, not just the visual color of an object, but about the chemical bonds that are present. So if you've watched true crime TV shows and they find a red thread at the location of some crime, and they go find some person and match that red thread to the specific threads that are in the person's jacket, that's an example of doing spectroscopy. They put both in a lab, they shine light on it, they collect the spectra, and they say, yes, this red thread is the same chemical composition of the person's jacket, right? So unless somebody bought the same exact model jacket from a store, you have a good chance that that's the person that committed the crime. So we're doing the same thing. We're collecting spectroscopy data. So each pixel has a spectra. So you can determine the chemicals. It's really the chemical bonds and the vibrations in the chemical bonds that determine the values you measure in the hyperspectral image.
And can you say a little bit more about the difficulties of collecting these data? Why is this a challenge, and what makes it particularly interesting for you for this work?
The biggest challenge, which I love, is that there are hundreds of thousands of different chemicals in our physical world that we interact with, right? If you walk down the street, you'll see roofs of cars, roofs of buildings, tarps, people's heads, hats, clothes, asphalt, cement, brick. There's a long list of all the different materials that you'll see. When you collect a hyperspectral image, in each pixel, you get a measurement of the chemical spectra for all of the different materials that are in that pixel. So what you have to do is what we usually use regression or something that says, I have this pixel, I want the abundances of the chemicals that are present. The problem is if you have 100,000 different things that might be in there, and you do a regression problem with 100,000 different regressor variables, and you only have 200 bands or features, you have an ill-defined problem. Mm-hmm. So this is where a lot of the Bayesian methods and the research come in to be able to handle that type of difficult problem. So it's a overabundance of information, right? You're getting every chemical that's on the ground in the area that you've imaged, right? So you can get a sensor that takes one image that covers Charlottesville, but how do you get all that information out of that image?
Yeah. So say a little bit more about how you get this information out of the image. You mentioned Bayesian methods and some things. So what is it? Can you give us a little more perspective on what you do in order to get that information?
Yeah. So the first thing you have to do is define what problem you want to work on. Mm-hmm. Right. So if you have a specific material you're looking for, so for example, one of the projects I worked with was looking for IEDs in Afghanistan and other countries, right? So, and it's a demining operations that are important to Ukraine right now. So this type of application, you've got an explosive object that's dangerous, and that's what you want to find. So you collect your image, and you want to say, where is that object? You don't care about the other 90,000 chemicals that are present. So for that type of method, typically you'll use what's called a target detection algorithm or a match filter as your first process on the image to find the pixels that have some similarity to the target you're looking for. And so that's similar to what we use when our phone gets a GPS signal. The GPS signal is much lower in amplitude than the background noise coming off the satellites. But because you know what that signal is, you can find it out of that background noise. And that's really a signal processing algorithm. So first stage for that is target detection. Where are my pixels that correspond to what I'm looking for? After that, you do further, more detailed analysis on those pixels that lit up in your target detection process. So that's if you're going after a specific target. Sometimes you want to take a hyperspectral image over like an open pit mining facility. Right, you want to know what are all the different minerals that are present in this area and where are they present, and show me the layers, because the structure of those determines, from that you can infer the geothermal activities that went on that created the things that you care about, right? So for that, we do often some sort of unmixing on every pixel in the image, and you get abundance maps that correspond to the image that show you the abundance of each of the minerals you care about across that image.
So what does unmixing mean?
So unmixing means, so we'll talk about mixing first, okay, and then we'll do the unmixing part. So if you think about a pixel in an image as a square in the ground, mm-hmm. right? Just put it out, picture that square out in your yard. There's probably some grass in that pixel, and there's probably some places, if your yard is like mine, where you've got bare patches and you can see the soil. So the spectra you measure for that pixel will be maybe 50% grass and 50% soil. Sometimes in my yard, it's 20% grass and 80% soil, but whichever. If you also put a red jacket out there in that pixel. The pixels tend to be big. So if this is like a 1 meter by 1 meter pixel and you put a red jacket in that pixel, your measured spectrum would be 0.3 times a red jacket plus 0.35 times grass plus 0.35 times soil, right? Those numbers add up to 1, given the different fractions of the area covered in that pixel by those different materials. So that's what mixing is. Unmixing is, if you're given the pixel, how do you infer what are the materials that were present in there and the abundances for those materials? It's not very hard if you know, okay, I know these 3 materials are in this pixel, right? There's plenty of standard methods to say that, right? It's linear regression will give you those coefficients. But when you say, here's a pixel, here's 100,000 candidates materials, which maybe 3 or 4 of these are present, that becomes a much harder problem. And that's the part that I get excited about. That's where the Bayesian methods come in and sophisticated algorithms to make those decisions.
Yeah, I imagine it must be even more difficult because out of that 100,000, there may be another 20,000 of things that you haven't even considered. Like the red jacket, for example, in your environment, you might not even have thrown that in as a possibility. So,
exactly.
Yeah,
one of the hardest things, and this always comes up in Bayesian methods, that is, how do you measure the probability that you don't know, that something is in there that you don't know? And so I worked with MITRE on that topic for our Bayesian model averaging. We patented a method for computing the probability using a Bayesian model averaging framework that it's not something we know, that it's something we don't know.
Yeah, exactly. Well, okay, I can see how you do this for surface materials, but you mentioned IEDs and they're buried. So how do you get at that?
So we can detect minerals with hyperspectral imaging. So I'm going to start with minerals because it's an area I can talk about without restriction, right? If you have an area and it's 98% clay and quartz and just stuff that's not very interesting, but 2% something that you care about, and I have a project I'm working on looking for lithium mines. Lithium's really important right now. 2% of the mineral that contains lithium, 90% of other stuff, you can, with the methods that we've developed, determine that, yes, that's that 2% of that thing that I care about is present. So you can work with very trace amounts of material. So you don't need like a physical object. You can have, if you're talking with grains and sand or powders or whatever. So anything that's left on the ground, even a small abundance, you could walk up to the place with your eyes and go, oh, there's nothing here. But we can still find it in a hyperspectral sensor because we're looking at the bonds outside of visible wavelengths, even at small abundances.
Yeah. So tell me a little bit more about the applications of this hyperspectral to other areas that you're working on now, because the stuff you did for the military was in the past. And what are you working on now that's got you excited? So
right now I'm working with landscape architects, particularly Michael Legering in the landscape UVA School of Architecture. And we're doing what's called engineering with nature, right? And so the idea is, we want to do urban planning on a large scale, right? We want to plan the growth of Washington, D.C. and Baltimore and the surrounding areas around the Chesapeake Bay region, right? Similar to the islands you were talking about. We have a project with Puerto Rico looking at how do we build, and the general question is, how do we build infrastructure that's going to work with the natural systems that are there and not against them? Not forcing, for example, a river to flow down a straight concrete canal, but building a space where the river can ebb and flow and erode its banks and move around and have a natural path, which is both more appealing to the human interaction with the environment, right? The kind of social space we build, but also is less likely to cause serious erosion damage, is less likely to cause flooding, is less likely to cause a lot of the things that come about when you force natural systems to conform to straight lines. Yeah, well, this is great. That sounds like a wonderful objective. Now, how does hyperspectral imaging? That's a really good question. Yeah. So to do that, right, so there is currently no way to say what are all the natural systems in the Chesapeake Bay region. There's just no answer for that. If you look at environmental scientists, they'll do experiments, but it's not really an engineering endeavor, right? It's an experiment to know how a plant will respond to a certain type of stimulus. Right. But the questions that come about when you want to do engineering with something are very different than the scientific experiments. So we're using the hyperspectral imagery to get the type of information you want to do engineering on that scale, which means we want to know all the different plant species. We want to know all the different soil types and erosion patterns and be able to infer all of those systems that are going on. And so here's an example. So beach grass grows on top of sand dunes. So you can infer erosion patterns by looking at the locations of beach grass because you can see the sand dunes. And if you monitor that over time, you can discover the changes in those erosion patterns. Now, my niche is taking the hyperspectral data and turning it into information. Like, where are the species? Where are the different soil types? Where does flooding occur? The landscape architecture people turn that into how do we make decisions about urban planning so that in 50 years, we're not fighting against erosion. We're working with the incorporating the natural systems with our urban planning.
Yeah, it seems like, but correct me if I'm wrong on this, it seems like you could also do the extended thing. You could not only look at what the natural system is doing, but you can look at how the human system has perturbed it. Is that right, or am I reading too much into this?
No, that's definitely right. Yeah.
Okay.
Yeah,
So, and that, it seems to me, would be absolutely critical to understanding the engineering aspect of how you fix that.
Yeah. So you're asking the question, thinking about, like, where have things gone wrong and how do we fix them, which is an important part of this. I think our focus is how do we build them so they don't go wrong in the future. But we need to fix the ones we have, too. I mean, that's definitely an important component of it, yeah.
Yeah, seems like it. Okay, this has been great, but let's move on to this other area that you mentioned earlier on, which is LiDAR. Tell us what LiDAR is and how we collect data in LiDAR.
So a LiDAR sensor is a sensor that sends out a laser pulse, measures the time until it takes that laser pulse to hit whatever it's going to hit, and return. And from that, it'll infer the distance to that object, which is, I don't know, the technology always amazes me that you can measure time at that fast of a scale, right? The speed of light going across a room or from an aircraft to the ground. Typically, you'll get information that's accurate to within a centimeter or a few centimeters.
So this is quite different. Well, I'd say different modality from hyperspectral in that one seems active and the other seems passive. Is that characterization that is used here?
Yes. Yeah. So active means we're sending out some kind of signal, usually electromagnetic type of signal. If you're doing radar or a sonar signal, which is a sound underwater, those are both forms of active remote sensing. We send something out, it bounces off what we care about, and we collect information on how it reflects back. Passive means we don't send out a signal. We use the light that's coming off the sun, or in thermal imagery, we might use the light that's coming off the black body radiation from the objects we're looking at, which depends on their temperature. So that's the passive. So hyperspectral is a passive form. LiDAR is an active form. Right.
And I guess one of the interesting differences here between the two is weather. If you fly your drone that you have on a very misty, cloudy day, it's a little bit more difficult to collect, isn't it, versus the LiDAR?
Yes, certainly. The hyperspectral will have trouble on a misty, cloudy day. LiDAR will have some trouble because some of your laser pulses will bounce off of clouds or fog or whatever and come back, and you'll get error measurements or non-physically realistic measurements. Interestingly enough, there's imagery you can collect using radar. It's called synthetic aperture radar, which you can collect if there's clouds or smoke or at nighttime because it's an active form of collecting imagery.
Right. Yeah, that's always been an advantage, I think, to that active form of remote sensing. Well, okay. So, what are some of the applications then that you've got for LiDAR? How are you using that for your research?
Yeah, it's a good question. So, I gave the beginning discussion of LiDAR, which is very similar to if you bought a laser tape measure at the hardware store. You can buy these and use them to measure distances across a room. But we don't want just one laser pulse in one distance. We'll put the LiDAR sensor on an aircraft or the drone. It swings back and forth or oscillates around or something, and it sweeps out and collects millions of laser pulses. And so what you get is a set of millions of XYZ coordinates for individual locations on the ground where that laser has hit an object. So if if that location on the ground is covered with vegetation, you'll get multiple hits at the height of that, whatever that vegetation is. And from that, you can infer leaf density, you can infer three-dimensional structures. So for us in the Engineering with Nature projects, the LiDAR gives us three-dimensional information about the vegetation species or the ground, and the hyperspectral gives us chemical information, the chemistry of what's there. And it's really one of the exciting parts to me is how do we combine those different sources of information that are very complementary to each other, but both very important.
Yeah. So do you use LiDAR? I mean, it seems like there's another difference here in that you've got the pixels. You've got the world pixelated for the hyperspectral, but now you've got these point values for the LiDAR. So tell us a little bit about how that changes your analytics and your processing of this.
Yeah, this is a really good question. So a lot of previous work that people have done, including myself in LiDAR, they take the LiDAR, they imagine taking a piece of graph paper and putting it over the ground, and they bin the laser pulses that hit in each square, and they turn it into images from that. And then you can do like the maximum height in each square, the minimum height, the standard deviation, the height, things like that will give you some information. It's a more complicated question. How do we use not just that binned version, but the full three-dimensional structures? So I have a master's, one of our MSDS capstones in our program is looking into how do we use convolutional neural networks. First, we're going to do the binned version, which is, it's not quite, doing that with the convolutional neural networks the way we were doing it isn't standard, but we're doing like one step up from standard. But then we're going to do the more advanced, which is a much larger research project of how would you handle this 3D information in its native, set of XYZ coordinates.
And are you doing this for specific applications as well?
So we have the LiDAR sensors for the Engineering with Nature program. In the online master's degree capstone, we're going to be working with LiDAR data that was collected over Haiti after the 2010 earthquake. And anybody who's interested can look up RIT 2010 Haiti earthquake LiDAR data, and I'll probably get a link to the Open Data Portal. They have a really nice web-based viewer where you can go in and zoom around and pan around and see the damage from the earthquake in the different buildings in Haiti. So we collected, it's a few terabytes of LiDAR data. This was my former institution where I was math professor, where we collected a few terabytes of data over Haiti in LiDAR after the earthquake. And so we're going to be looking at that to see what we can determine to find different objects and then determine information about those. That's going to be the goal of that project.
Now, when you work with LiDAR, do you work with that as like a entirely separate source, obviously, from things like hyperspectral? But is the analysis strictly then in LiDAR to get, for instance, the damage, or do you combine it with the hyperspectral as well?
Yes to both.
Okay.
A lot of the work I do requires government collaborations and corporate collaborations, and there's just a lot of partners involved to get all of these things done. So the company that makes the sensors we use is called Headwall, and I have a bunch of collaborations with Headwall. Some of their people are former students of mine. It's a good relationship, and they build the LiDAR sensor or integrate the LiDAR sensor that it's a Velodyne sensor with the Headwall hyperspectral sensor on the aircraft that we use. And then their software combines the information too. So it creates the hyperspectral image, but then it adds a few bands, which are the information from the LiDAR, things like the mean height, the max height, the standard deviation. So you can work with them together in a single data source. The nice thing there is that they're co-located physically on the ground, right? You have a measurement of a spectra from the leaf of a plant, and you have the LiDAR information for that same location. Right? You can work with them separate, but it's really nice having them together.
And that was the question I was going to ask you, and let me ask it this way. It seems like you need really good resolution to make sure that these things can be combined that way, so you know that this plant is the same plant in both images. So how's that accomplished?
Yeah, it's advantageous when you have the two of them collected together, and that's done with lots of software.
Yeah,
and then is lots of software in engineering, right? Because you have to know what's the angle that my hyperspectral sensor was looking, and then you set a target up. To do it well, you set a target up on the ground that you know is a square, and then you adjust all those. You take a first initial guess that the sensor has, but it's on a drone. It's not exact. It's based on the GPS, which when you collect your initial GPS, it's not accurate enough, but you can post-process to improve the accuracy of your GPS. So it's putting all those systems together to get that information.
So it'd be more difficult to do than if, say, somebody else collected one of those. Let's say someone else collected the hyperspectral, you collected the LiDAR, and then you tried to put them together. And it would be even more difficult if they was separated in a lot of time, right?
Yep. Yeah, that becomes more difficult.
Yeah.
When they're separated time, or even collected by different people over the same location. For the Haiti earthquake data, we also have high-resolution visual imagery. One of the things that happened after that earthquake, blue tarps were given out to people whose homes were damaged, and they made these makeshift blue tarp villages. Right? So one of our master's degree programs, our statistical learning class, uses the visual red, green, blue imagery from Haiti to locate those blue tarps, to build methods for locating those blue tarps. So one of the things I'd like to do is to have those locations of blue tarps from the visual and combine those with the LiDAR that we're going to be working in with the master's degree capstones. One of the paths that we might pick if the students are interested.
Yeah, that sounds really, really cool. Okay, what other things can you tell us about taking LiDAR into information? How do you tell us more about how you actually do that for these problems?
In what respect, like physically how we collect it?
No, analytically how you do it. So in other words, what is it, you explained to us in some great and efficient detail how you do it for hyperspectral. And you gave us a rough overview of how you're doing it for LiDAR, but tell us a bit more about how you take the LiDAR data and convert it into information. For instance, it can be used by your, it was the Engineering with Nature projects.
Yeah. Okay. Yep. So currently the best way to deal with it is still to grid it and put it in discretize the X and Y coordinates. Mm-hmm. So think about putting in a grid and you have all your Z values for each square. And that's a very good way to work with it. One of the things I've done is taking an image over a city area and then labeling each of the pixels, because at this point they're pixels, even though instead of having some color values in them, they have an unknown number of LiDAR pulse heights for that pixel, right? But you can still think of it as a pixel. And you have to build your ground truth. And so the ground truth for the test that we worked on, so I'll explain how this works. We had street lights, cars, people, 4 or 5 different types of vegetation, 4 or 5 different types of buildings. And then asphalt and unkept fields, and then sports fields. So you can imagine different heights of grasses or textures on those. And so what we did is we labeled, actually my daughter did this, labeled lots of the data in the imagery. And then so what you wind up with is maybe 100,000 pixels that you know what they are. For each pixel, you have...
Really? 100,000 were labeled?
Yeah. Yeah.
Your daughter is really a hard worker.
She is a very hard worker. This is true. Or maybe I'm not such a nice dad. I don't know. And for each of those, you have the max height, the min height, the standard deviation and the heights. You could do an expectation maximization and model that distribution with a couple of Gaussians vertically if you wanted to do something a little fancier. We didn't do that. And then for the neighboring pixels, we also incorporated sort of max height and min height around the area. So not only, are we measuring the height of the thing we're looking at, but the height of the surrounding area around it. So like a street lamp would have a max height of maybe 30 meters and a min height of 0, right? Because it's tall and skinny, and the area around it wouldn't have anything high. Edge of a building would have a max height maybe of 30 meters and a ground of 0, but it would look differently in the neighboring pixels. So you build that information up. And we used, what we found that worked best was a random forest, which makes sense because it incorporates decision trees, because streetlights are a fixed height, right? You would get this relationship and you could set a threshold and say anything that behaves in a certain way that has a max height of over 30 meters would be a street lamp. And so you can build it out and get the categories. Height of a person would be, 3 feet to 7 feet, right? Things that hit in that range that have the right area around them would be a person. And so random forest worked very well for that.
So I can see where you can do this kind of thing. You could take your results and apply them to another place that has streetlights and asphalt and so forth. But you can't apply it to, I'll just say, the problem I gave you earlier, the barrier islands, has none of that. And do you have to go back to your daughter every time and get 100,000 ground truth?
So this is part of the engineering with nature part. We don't want to look at just one location and be able to repeat on that location. So one of the things we're doing is we're planning we're coordinating with the the FDA to get species and seeds that correspond to specific plants that we care about.
What is U.S. FDA?
FDA, Food and Drug Administration.
U.S. Food and Drug Administration.
Yeah, and there might be another group that's partnering with us. And so there's too many partnerships, remember?
Okay.
And I'm bad with acronyms, so I apologize. But we collaborate with both industry and government to make sure we know the species we get and that they're pure. And then we plant them in different soil conditions, and then we kind of torture them by spraying salt water on them and measure their change throughout a whole year. So this is why we spend a lot of time down at Morven Farms, because we want a very controlled measurements, but out in the wild, of how these things respond to different conditions. Once we have those measurements, then we can go to the Barrier Reef Islands and look at the conditions there and say, oh, this in May looks like a certain area over here, and we know in May the species that are there are in a certain stage of development and growth through their annual cycle, and so we can compare them and understand what's going on.
Okay. Well, why don't you tell us a little bit about the current and future challenges? You've told us some about the current ones, I guess, but tell us how those bleed into the future challenges that you're up against.
Okay, I hate to admit it, but the one challenge that keeps me up at night is that in hyperspectral image, vegetation is dominated by chlorophyll. So the spectra you get, right, you can tell very specific about, for example, polymers. You can tell a low-density polyethylene from a high-density polyethylene with near absolute certainty, as certain as if you were standing and looking at it and reading the tag on the garment, right? And you can do that from an aircraft or from space. But vegetation, the primary source of what you're looking at and you get in your spectra is chlorophyll. So there's a high correlation between spectra from vegetation, even from different species. There's a little bit of variation, but I don't know if the variation of a fixed species throughout the year is different than the variation from another species. And this is what you see if you look at, I don't know I like watching spring, watching the different things come out. In early spring, when things start to come out green, you'll get a lot of variation in the green of the things because they come out at different rates and respond to the weather in different ways. Mid-late summer, everything is generally a lush looking green, right? Pine trees are a little different from oaks and elms and et cetera, but you get a more consistent green. So I'm not sure about doing that unmixing part when the spectra for the things you care about are highly correlated to each other. I don't think anybody solved that problem yet. I don't know if enough people are aware of that problem. Because when you do a controlled test over one location and you take your ground truth from that location and feed them back in, you can do quite well with just about anything, right? But how do you do that robustly over time, changing seasons? That's a harder question.
Yeah, that's great. And any other comments on other applications you're thinking about, other future applications of this work?
The mining, like natural resource, is a very interesting one. That's interesting because there's both the chemistry of what you collect in the spectra, but the geological processes. So lithium, for example, one of the things that's interesting right now because of the growth of electric vehicles that require lithium for the batteries, currently not enough lithium in the world that we have access to build batteries for the electric vehicles that we plan to build and run, right? So lithium is often found in minerals that are formed by a geological process that goes something like the following, right? So when molten rock is hot underground and it cools, you'll get large grains. So if you look at a lot of the granite and the rocks we see around in this area, you'll see like large black dots among white, right? And so that's an igneous rock that was formed by cooling, slow cooling underground. Cooling of molten rock above ground gets much smaller grains, much smaller grains than those. Lithium is formed when there's molten rock that contains the right compounds to begin with, and it cools slowly, but it's held under pressure, which if you've seen like a bottle of some beverage that's left in the a bottle of some beverage that's left in the fridge and it cools below freezing temperature, and somebody picks it up and then taps it and the whole thing freezes right away, right? Mm-hmm. It's same phenomena with these rocks. They're underground, they're under pressure, they don't solidify at the normal temperature. They're held at the more molten temperature. And then once crystal starts to form or something disturbs it, they transition, they go through that phase change to a solid fairly quickly, and the lithium is pulled into the crystals at that time. So you're looking for these specific crystals and this specific activity type of thing, and you're trying to infer that. So that's one of the projects that I think is both really important to humanity in figuring out how we're going to run electric vehicles for their benefits, but at the same time find the lithium we need to be able to do that.
Yeah, that's great. Well, thank you very much, Bill. This has been wonderful to talk to you.
Thank you very much, Don. It's been my pleasure.